For years, bypassing video game copy protection was a frictionless experience for the end user. You would download a small executable, replace the original file, and the game would run. Protection models like the standard Steamworks API operated on a simple logic gate. The software would query the platform to confirm the user owned a valid license, looking for a basic yes or no. Reverse engineers bypassed this by using open-source emulators. These programs acted as a middleman, intercepting the query and handing the game a spoofed yes response before the software could ever reach the official servers. Then, Denuvo arrived. It abandoned the simple external license check in favor of a system that integrated itself directly into the game's machine code. The impact was immediate. Major titles that would typically be bypassed within hours of launch suddenly remained secure for months, and in some cases, years. The community of reverse engineers realized they were no longer dealing with a simple gatekeeper, but a system that constantly verified its own integrity while the game was running. Understanding exactly how this complex system works requires moving past the user interface and diving deep into the machine's architecture. On boot, Denuvo queries the Windows kernel and CPU ID instruction to collect specific hardware strings from your motherboard, CPU, and storage drives. This mathematically generates a unique hardware fingerprint. A remote server processes this, returning an encrypted local license file. This hardware binding changes the nature of the game's executable. It is no longer a universal program. It is modified to run exclusively on one specific tower. Beyond the hardware check, the protection moves into the game's core instructions. Denuvo replaces essential game bytes with proprietary virtual machine bytecode. If runtime hardware identification doesn't match the license file, the machine fails to decrypt the stolen constants, immediately crashing the game. To prevent tracing, bit vectors scatter this data across thousands of unrelated memory addresses. Crackers counter this by using disassemblers like IDA Pro to meticulously locate and map out every single scattered virtual machine handler in the code. They employ Z3 theorem provers to perform inverse calculations, using heavy math to derive what the original stolen instructions were before they were encrypted. Cracking the system is the grueling, microscopic assembly of a fragmented logical system. Once a reverse engineer finally reconstructs the logic and bypasses the hardware check, the finished result is released for free. This work is conducted within The Scene, an underground network of release groups that has operated in the shadows for decades. The Scene is governed by strict Scene standards. These are rigid requirements for how a crack must be managed and uploaded, ensuring that only the most efficient and reliable releases are accepted. Every release includes an NFO file containing technical details and group greetings, often accompanied by cracktros, complex programs featuring music and digital art that serve as a signature of the group's technical skill. The process ends with a race to upload the file to hidden FTP topsites. The first group to upload a working, standard-compliant crack earns the pre, while slower groups are ignored. As corporations build more complex layers of virtualization, this subculture continues to dedicate hundreds of hours to deobfuscating them, driven by the intellectual prestige of defeating the most sophisticated protections in the world.